Welcome back. Today we will start discussing the topic of DTMCs with countably infinite state space. All right. So, we are going to discuss countably infinite state space Markov chains in discrete time. Okay. So, the Markov property is satisfied, but the state space S is something countably infinite. So, without loss of generality, we can take it to be 0, 1, 2 dot dot dot. All right. And the Markov property is satisfied in the sense that p x n plus 1 given x n minus 1 dot 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 x naught is still just equal to p x n plus 1 given x n. Okay. This is true for all values of n greater than or equal to 1, n greater than or equal to 0, and for all values of state space, values of x n in the state space, right. So, we will continue to denote p x n plus 1 equals j given x n equals I. We will continue to denote it as p I j as before. Now, in this situation, the transition probability matrix is not really a matrix, right. It is an infinite by infinite dimensional object, right. For this reason, we cannot use these matrix analysis techniques or linear algebra techniques or spectral techniques in a very straightforward manner as we did it in the finite state case. We cannot directly apply those kind of results to the countably infinite state space Markov chains. Okay. This is mainly because the spectral theory and the linear algebra of these infinite dimensional operators is far more involved. All right. So, the matrix approach does not work. For countably infinite state space. All right. So, if you want to study things like long term behavior etc., so we have to go for a different kind of an approach. All right. So, in fact, the approach that works is by looking at first passage times and recurrence times. Okay. So, what you do is we already discussed first passage times in the context of in the previous lecture we discussed how to calculate expected first passage times and expected recurrence time. So, first passage time means you start at I and what is the first time at which you get to state j, all right. Recurrence time of a state j is the time you start at j and the next time you return to j, that is the recurrence time. We learned how to calculate the expected first passage times and expected recurrence time of a state in the previous module. In this particular approach, we will study the random variable of the first passage time and the random variable of the recurrence time, all right. As we shall see, this random variable may not really be a random variable in the sense that they may be infinity also, in that case they will be defective, but these quantities, the first passage times and recurrence times, will help us study these the properties of countably infinite state DTMCs. In fact, we will use first passage times and recurrence times in conjunction with results we know from renewal theory. Renewal theory applied to Markov chains. Okay. These two tools together will help us study these countably infinite state Markov chains. In fact, everything we are going to say for countably infinite state Markov chains also applies in an easy way to finite state Markov chains, but not everything we said for finite state Markov chains will apply for countably infinite state Markov chains. Okay. All right. and we will see that the notion of recurrence, transients, etc., are also defined very differently for a countably infinite state Markov chain. Okay. So, let us define the first passage time probability. Let us say f I j of n is defined as the probability that x n is equal to j, x n minus 1 not equal to j, x n minus 2 not equal to j, dot 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 x 1 not equal to j, given x naught equals I. So, you are starting the Markov chain at time 0 in state I, all right. First passage time probability means I should be in state j at time n for the first time, all right. Please keep in mind that this is different from Pijn, all right. So, this is different Pijn, which we defined as the probability that I am in state j at time n given that I started in state I at time 0. I am not requiring in this case Pijn case, I am not requiring that I be in state j at time n for the first time. I just want to be in state j for at time n, all right. I could have been in state j before also, this Pijn allows for it, but Fijn is looking at the probability that I am in state j at time n for the first time, and the previous times I was not in state j given that I started at state I, right. So, this Fijn is a first passage time probability. Okay. This will be useful for us to study. Okay. So, this Fijn also satisfies a equation very similar to the Chapman-Kolmogorov equation. This is sort of an iterative sort of an equation. It's as follows: Fijn can be shown to satisfy sum over Pik k not equal to j f kj of n minus 1, and this is true for n greater than 1, and for Fij of 1 is simply Pij. Okay. So, Fij of 1 is nothing but the probability that you will be in state j at time 1 given that you started in at state I at time 0. This is nothing but Pij, but for n equals 2 onwards you have to exclude this this k not equal to j is important. Okay. So, Fij of n is given by sum over k not equal to j Pik Fkj n minus 1. So, Fkj n minus 1 means you were in state k for the first time at time n minus 1, and you jumped sorry you went from I, sorry let me say this again, the sum on the right should be interpreted as you started at time state I, you went to some state k, all right, and from state k you went to state j at time n minus 1 for the first time, all right. That is what this equation means. This is an iterative equation. So, you solve, you set Fij equal to 1, Fij of 1 is equal to Pij, then you iteratively solve for Fij of 2, and then you go ahead and solve for Fij of 3 and dot dot dot, all right. So, these are the iterative equations governing these first passage time probabilities. These are not this is not difficult to derive, all right. Similarly, let us define big Fij of n as sum over m equals 1 to n little Fij of m. Okay. So, Fij of n is the probability state j occurs at some time between 1 2 dot 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 n 1 through n given x naught equals I. So, little Fij of m is the probability that I start at I and reach j for the first time at time m, right. Now, I am summing over all these times from m is equal to 1 to n. So, this big Fij of n should be interpreted as the probability that state j occurs at some time between 1 and n inclusive 1, 2, 3 dot 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 n given that I started at I, x naught is equal to I, all right. So, this is also a probability. Okay. So, remember these the events that define Fij of n are disjoint over this n, right. So, I basically this probability interpretation for this big Fij comes from summing over disjoint events, all right. Now, if you look at this Fij of big Fij of n, right, what can you say about it? Fij of n is monotonic in n, right. That is because you are adding these non-negative little Fij's. So, Fij of n is monotonic in n, right, and it is upper bounded by 1. So, why is it upper bounded by 1? Because if you reached if you started at I and reached j for the first time at time 3, you cannot also start at time I and reach j for the first time at time 5, right. So, that is not possible, right. So, what happens is that this Fij of n will be is a quantity which is monotonic in n, which is clear and is also upper bounded by 1, right, being a probability. So, what happens is that this limit n tending to infinity Fij of n exists, all right. Let us call this limit as Fij infinity. Okay. That is just notation for limit n tending to infinity Fij of n, which exists because Fij of n, big Fij of n is monotonic and bounded above, right. So, the limit has to exist. So, Fij of infinity should be interpreted as the probability that state j occurs eventually given x naught equals I. Okay. Fij n is the probability that state j is reached between 1 through n starting at I. Now, if you take limit n tending to infinity, this Fij of infinity should be interpreted as the probability that state j is eventually occurs given x naught equals I, all right. And in particular, so if you can look at it this way. So, if Fij of infinity equals 1, then state j occurs eventually with probability 1 given x naught equals I, right. If this is less than 1, then there is a positive probability of never returning to state j, or never returning is not the never going to state j given x naught equals I. all right. So, the Fij of infinity, so this limit exists, and Fij of infinity could be some number, it is certainly a number which is at most 1, right. It could be 1 or it could be less than 1. If it is 1, it means that the probability of eventually seeing state j given that I started at state I is equal to 1, which means that almost surely I will see state j given that I started at I. If Fij of infinity is a number which is strictly less than 1, which means that the probability of eventually going to state j given that I started at I is strictly less than 1, which means there is a strictly positive probability that I will never see state j given that I started at I, all right. Now, so these quantities are, this Fij infinity is a very useful thing to look at. In particular, if you look at this guy Fjj infinity, right. What is Fjj infinity? Given that I start at j, what is the probability that I eventually see j again, right. So, this is the probability that I come back to j starting at j, right. If this probability is equal to 1, right, then return to state j happens with probability 1 having started at state j, right. And if Fjj infinity is less than 1, in this case there is a positive probability of never returning to state j having started at state j, all right. So, 1 minus Fjj infinity will be the probability that you never return to state j having started at state j, okay. Now, using this characterization of Fjj infinity, whether or not it is equal to 1 or less than 1, we can define the recurrence of a state, okay. Remember that in the finite state case, we defined recurrence very differently. We said that a state is recurrent if for every state that you can get to from that particular state j, there is also a way to come back, right. That is how we defined for finite state Markov chains. That definition is inadequate for the case of countably infinite state DTMCs, okay. So, we need an altogether different definition of recurrence and transients, and we will give that definition using this Fjj characterization, okay. Definition. A state j is said to be recurrent if Fjj infinity is equal to 1, okay, and a state j is said to be transient if it is not recurrent, that is Fjj infinity is strictly less than 1, okay. So, if this is your discrete time axis, let us say you are in state j at this point. So, you may go through various states, all right, L, K, M and so on, and return to j again, right, again some other state K, P, etc., and then return to j again and so on, all right. So, you look at all these returns, all right. So, you start at time 0 you start at j, right. This is time t equals 0, you start at j, all right, you go through bunch of states and then hit j again. So, if you look at if the situation is such that fjj infinity is equal to 1, then you are guaranteed with probability 1, you are guaranteed that you will come back to state j, all right. If fjj infinity is less than 1, there is a positive probability that you will never come back to j, all right. If fjj infinity is equal to 1, which means that you are guaranteed to come back with probability 1 to state j, having started at state j, then the times between these times, if you look at these times, these guys, right, they can be looked at as random variables, right, because in finite time you are guaranteed to come back, right, with probability 1. So, these times between consecutive occurrences of state j will be finite with probability 1, right. If fjj infinity is equal to 1, the time interval between consecutive, let me write it like this. We know a term for this, right? This is called the this is called the recurrence time, right? The recurrence time of state j, meaning that you start at j and come back to j, will be a legitimate random variable, right? It will be finite with probability 1, right? And I can denote this as tjj, okay. So, this tjj will be less than infinity with probability 1 in this case, okay. If fjj infinity is strictly less than 1, then this tjj will be a defective random variable, meaning that probability that tjj is less than infinity will be less than 1, okay. In other words, tjj can be infinity with positive probability, and if you remember, random variables are generally defined to be real valued, right. You are not allowed to have infinite value with any positive probability, right. Such a random variable is not really a random variable, it is called a defective random variable, all right. So, this tjj in that case will be a defective random variable if you are not guaranteed return to j with probability 1. If fjj infinity is equal to 1, with this recurrence times between consecutive returns to j will be finite with probability 1, and you can define a random variable tjj, right, and this will be finite with probability 1, okay. So, this tjj is a very useful thing to look at, okay. Now, we can show that this definition of recurrence is sufficient to accommodate both countably infinite state Markov chains as well as finite state Markov chains, okay. This definition will fall back to your original, is equivalent to your older definition for finite state case, but the older definition will not apply for the countably infinite state case, okay. This can be shown. So, maybe I should say applies to both finite and countable state space DTMCs, okay.